Hope everybody's having a great reInvent. My name's Mark Olson. I'm a principal software engineer focusing on storage and virtualization, and this is the deep dive on Amazon EBS. And I've got
Jody Gibney. I lead a product management team for EBS, so I'll be doing the first part of the session. Anyway, to kick it off, I wanted to start by just touching really quickly on the three main types of storage services that AWS offers. So storage, obviously the best one, where your operating system is interacting at a byte level with a device transferring data in fixed block sizes. So obviously EBS is the service that equates to that. Then we've got file-based storage, and with file, rather than interacting directly at a byte level, you're abstracted up a layer using file system semantics like NFS. So our service there is EFS. Then lastly, there's object storage, which is abstracted up even a layer further, and there your application talks with a RESTful interface like HTTP with a web service with APIs. So within block, we've got three main types. There's EC2 local instance storage, then there is SSD-backed EBS volumes and HDD-backed EBS volumes. So just first, a couple notes on instance storage. How is it different? First of all, with instance storage, you're dealing with physical disks. These are local to the physical host that's hosting your instance, so they act exactly as you would expect a locally attached HDD or SSD drive to behave. This is not persistent storage, so your data will not survive an instance stop or termination, although it will persist through a reboot. And data is not replicated by default. There is no integrated support for backups like with EBS snapshots, and there's no out-of-the-box encryption. However, if you want any of those three things, you can go ahead and build it yourself on top of local storage. So how is EBS different? EBS is block storage as a service. With an API call, you can configure a set amount of volume blocks with specific performance characteristics and attach them to your EC2 instance. It is a service delivered over the network, so that's important when sizing your instances and thinking about performance. But most importantly, it is a service, it is not a drive. So EBS does not act exactly as you'd expect a local HDD or SSD to behave. We don't go, when you call our API, and grab an SSD and say, okay, this one's for you. Rather, EBS is a massive distributed system. Your EBS volume is a logical volume that's comprised of blocks that are spread across many, many, many physical devices. But because we're a distributed system, we're able to offer performance and availability characteristics that are beyond what we could if we were just mapping a volume to a drive specifically. So EBS exists in a single availability zone. Volumes are entirely independent of EC2. So this is persistent storage. You can blow up your EC2 instance, your EBS data will still be there. But most importantly, I think, EBS allows you to right-size the exact amount and type of storage that you want with the exact instance that's right for your workload. So you don't have to go with whatever instance and storage happens to be bundled with your storage-optimized EC2 instance. You can detach and attach a volume to another EC2 instance within the same availability zone. And the benefit there is that it allows you to recover gracefully, for example, from instance failures. So a little bit more on EBS. You can attach EBS volumes to only one EC2 instance, but you can attach a ton of EBS volumes to a single EC2 instance. And people regularly do that when you need more performance than a single volume can provide. We do recommend that you separate your boot and your data volumes. So keep your boot volumes small, move your data volumes around as necessary. I'm going to go in a little more depth on the EBS volume types. So we've got two main types of EBS volumes. There is solid-state drive-backed EBS volumes and hard disk drive-backed EBS volumes. And there are some differences that are related to the physical characteristics of the underlying media. So take SSDs, for example. With SSDs, they're flash-based, so there are no moving parts. The more banks of flash you stack in, the more parallel I/O you can drive to an SSD. All points on an SSD are equally accessible, which makes them fantastic for random I/O. Now contrast that to HDDs, where you do have a lot of moving parts. In order to read your data, you actually have to move the disk head to the location you need to get to. And that movement, or seek times, are some of the most expensive and performance-impacting actions you can take on an HDD, which make them absolutely terrible for small random I/O. On the other hand, once you do get that head into the right place, HDDs allow you to get fantastic throughput performance on sequential I/O at a really, really low price point, which is why we recently introduced 2 new HDD-backed volume types, which I'll talk about later. So here's the whole portfolio. On SSD, we've got GP2 and IO1. On the HDD-backed volumes, we got ST1 and SC1. How do you choose the right volume type? The first and most important consideration is what aspect of performance is most important to you? Is it IOPS or throughput? If it's IOPS, then the question is, well, how much? If you need over 80,000 IOPS, which is the current EBS-optimized maximum, then you want to go with something like an i3. If you're okay within what EBS can do, then your next question is one of latency. Do you need microsecond latencies? If so, again, go with a local SSD. If you're okay with millisecond latencies, then you've got a cost versus performance trade-off. So if cost is more important for you, then try out GP2. Sorry, my voice is going a little hoarse after several days in Vegas. So GP2 works for almost any workload. Truly type, like okay? General purpose. Yeah. Can you figure out what? I need to move it. Is it okay now? All right. So it's a general purpose volume type, and we designed it to be that way. So in 2014, when we were making GP2, our research scientists went out and profiled I/O patterns across the entire EBS fleet. And they ran a ton of simulations and modeling against that to figure out what the ideal performance specs of a volume had to be in order to meet about 90% of the workload I/O patterns we were seeing. That's how we ended up with the specs of GP2. So you've got a 3-to-1 IOPS to GB ratio, a minimum baseline of 100 IOPS, and most importantly, for volumes under 1 terabyte, you've got a 3,000 IOPS burst. The reason we settled on a burst model was because that was the type of I/O that we were seeing. We were seeing long periods of idle time followed by a momentary but really high spike in IOPS, which is why we decided to give even the smallest EBS volumes the ability to burst up to 3,000 IOPS. So these volumes are good for almost any kind of workload, boot volumes, pretty much whatever works pretty well on GP2. So what if this performance is your priority? In that case, look at IO1. So it's got about, as you can see, double the per volume performance specs as GP2, but there are 2 points about IO1 that differentiate it from GP2 and they're really important. One is IOPS consistency. So IO1 is designed to deliver within 10% of provisioned performance 99.9% of the time. And that's in comparison to GP2, which delivers 99%. And that 1.9 is an order of magnitude of difference in IOPS consistency. Similarly, in terms of latency consistency, IOPS is also much different. IO1 has a much narrower band of latency variation, so its latency is much more consistent than GP2, and you see a lot less jitter. So where that is relevant is if you've got a critical database that really relies on latency consistency and IOPS consistency, that's the time when you want to look at using IO1. It also scales pretty quickly. I mean, at 400 gigabytes, it meets its maximum per volume IOPS of 20,000, and that's because it has a 50-to-1 IOPS to GB ratio, which makes it great for small, hot data sets. So what if you care about throughput? In that case, the first question is, what is your workload like? Does it have majority large block I/O, sequential I/Os, or is there a lot of small random I/Os intermixed within it? If there's a lot of small random I/O, then you're going to want to go with an SSD volume. However, if it is majority large block sequential, then how much throughput do you need? If you need over 1,750 megabytes of throughput, which is the current EBS-optimized maximum, though keep an eye on those numbers because we're constantly increasing them, and this will probably be out of date in like 2 seconds, then go with something like a D2. But if you're okay within what EBS-optimized can do, then you have the same cost-performance trade-off. If you care more about performance, look at ST1. So ST1 is a throughput-optimized HDD-backed volume. Its performance is defined in megabytes a second because throughput is what's important, and it can burst up to 500 megabytes a second per volume. And these are great for big data analytics workloads like Hadoop, MapReduce, Splunk, log processing, Kafka, etc. But if cost is more important to you, then you want to take a look at SC1. So SC1 is a lot like ST1, it's just got slightly more modest performance specs. You can burst up to 250 megabytes a second, and the baseline is a little cooler. But it's useful for almost all of the same workloads, just in a slightly colder setting. So here's a whole which way adventure, but what if you just don't know, or frankly, you just don't care when I think about it? In that case, just use GP2. It works for almost everything. So I wanted to review a couple of examples about how customers have benefited from EBS's particular volume characteristics and also intelligently mixed and matched instance types with different types of EBS storage in order to optimize cost and performance. So Librato is a cloud metrics monitoring company, and CrowdStrike provides enterprise threat detection. Both of these customers were running their petabyte scale Cassandra clusters on I2s, and they decided to move to C4s, which are, with all that CPU, much more optimal for a Cassandra cluster, plus EBS. They put their hot files, their hot data files, on GP2, and then they put the majority sequential Cassandra commit logs on ST1, thereby getting the best performance possible at the lowest cost. For CrowdStrike, they saved about 50%, and Librato saved about 35%. They also benefited from things like the ability to scale. So they could go from an M4.4 when they had to scale to an M4.16XL and just detach their volumes and reattach them, and then detach and reattach the smaller instance when they're done. So there's a lot of flexibility there. Here's the whole lineup. We charge in per gigabyte month, which is now prorated down to the second. The only volume that has an additional charge here is IO1, which has the per provisioned IOPS charge on top of it. And you can snapshot anything for 5 cents per gigabyte month. So in February of this year, we introduced elastic volumes, which was a top customer ask among our base. Elastic volumes allows you to increase your volume size, to change your volume type, and to increase or decrease your provisioned IOPS. But most importantly, it allows you to do this when your application is actively driving I/O to your volume. And the benefits there are that there's no need for a maintenance window or downtime as you grow out your storage or increase IOPS. And then there's a big cost savings benefit because you no longer have to over-provision your storage because you don't want to take downtime when you grow it, or provision your provision IOPS for peak. You can just scale your IOPS up and down however you need. I'm going to go through a quick example of how to modify a volume. Because you're touching anything, we recommend that you first back up your volume, but then you just modify it, monitor the modification, and then extend your file system if you are increasing volume size. So you modify the volume using the EC2 modify volume command. Here I'm going from a 1 terabyte GP2 volume to a 5 terabyte IO1 volume with 20,000 IOPS. I use the describe volumes modifications command to get the status of my modification. I can see everything about it, what state it's in, how far along it's in. You'll notice that you really quickly go from the modifying state within a few seconds to the optimizing state. Once you're in the optimizing state, you've got the additional storage, and you can go ahead and resize your file system. So here, well, I mean, if you don't know what your file system is, you should check. Most of you, I assume, know. You can go ahead and compare your block device size to the file system disk usage, which will, in many cases, not reflect the increased size that we just did. Then you extend the file system. And it's worth noting that if your drive is partitioned, you need to first grow the partitions. So you can do this on Windows also using the disk management utility. Just go ahead, click on Action, Rescan Disks, then you right-click on the contextual menu, choose Extend Volume, and enter the target size in megabytes. And you can do that also on PowerShell. So a few tips. Modifications have to fit within the volume specs. So I can't create a 1 gigabyte ST1 volume because the minimum size is 500 gigabytes. You can modify volumes once every 6 hours. And if you're using current generation instances, you don't have to do anything except if you have an old volume attached that was created before November 1st, 2016, in which case you have to do a one-time stop, start, or detach, attach of the volume. So we've seen a ton of great automation ideas coming from customers and solutions architects using things like Elastic Volumes, CloudWatch, Lambda, EC2 Systems Manager. One interesting one is to publish a custom CloudWatch metric showing the free space on your OS, then use Lambda plus EC2 Systems Manager to automate the process of extending the volume and of growing the volume and then extending the file system. The other kind of things you could do are use a CloudWatch alarm to look for when a volume is getting close to its IOPS limit or exhausting its burst balance. We have a few examples that we've put up there on AWS Labs if you want to go ahead and take a look. With that, I will hand it over to Mark. Here you go.
Thanks, Jody. All right, so now that we know all about EBS volume types with Jody's awesome animations, I want to take a little break. Actually, if I can get a show of hands, how many of that was a review? Or how much of that was a review for people? If you've got experience with EBS, go ahead and raise your hand. All right, we got some new people in here, most familiar though. So you know that once you create an EBS volume, you need to attach it in order to use it. And to attach it, you attach it to an EC2 instance. Here's the API, CLI, and console commands. Specify the instance ID, the volume ID, the mount point. Now the mount point's going to show up on Linux when you're running on our Xen hypervisor. So instances that are built on Xen will show up at this mount point. I'll talk more about that in a moment. And Windows maps this to a bus ID. There's a complicated mapping that we've got in our documentation that you can find. So in Xen and Linux, you do an ls block. You see this XVDF, which is what I just attached. I'm not sure what I was doing with 1 gigabyte of data, probably just doing this demo. Can't do a whole lot with 1 gig anymore. So we see that attachment in there. And let's see what happens behind the scenes. So each instance on our Xen hypervisors are associated with an IO domain. Sometimes you'll hear this called DOM0 as well. Now this IO domain does not have access to your instance memory. Your instance doesn't have access to the EBS volume. So this is how so when you attach a volume, what happens is that volume is attached to the IO domain. A shared memory segment is set up that acts as a queue for IO requests between your instance and EBS. And there's really a couple more queues in there. I've simplified the picture. So when your application wants to do an I/O, it'll submit a system call to the kernel, whether that's Windows or Linux. They both act about the same. Different driver stacks, but that's fine. So in this case, we've got an 8K read. It gets put onto the queue, rings the doorbell to wake up the I/O domain. I/O domain wakes up, pulls it off the queue, puts it on another queue, sends it off to EBS. The response comes back in the other way. So hopefully you guys have had a chance to watch the talks by my colleagues Matt Wilson and Anthony Ligori. They went through a bit about our new Nitro system. So I'm going to go through some highlights right now as they pertain to EBS, but they do a pretty good deep dive talking about the new offloads that we've built. So in the Nitro hypervisor, to improve I/O performance, we looked at a number of different ways to bring EBS volumes into the instance. And what we settled on is NVMe, or non-volatile memory express. Now we use this as an interface because it's got a pretty easy programming model. The driver community at this point is pretty mature. But it is important to remember that even though we show up as an NVMe interface, the volume performance characteristics are based on your configuration. So this isn't like an NVMe drive that you're going to buy off the shelf. Just because you provisioned a GP2 volume, you're not going to get 100,000 IOPS out of it. So in Linux, you can use the NVMe. So if you do an LS block on these, you'll see this bunch of NVMe 1N1 and kind of confusing nomenclature. This is how the Linux driver stack decided to enumerate NVMe devices. Since we're a PCI controller, though, we're able to present a lot more information than the old Xen paravirtual drivers. And so we've set the model number of the NVMe controller to Amazon Elastic Block Store. And the reason for that is so that your AMI can programmatically determine the difference between instant storage on i3 or EBS volumes. For EBS volumes, we've added the volume number, or the volume ID as your serial number. We had to get rid of the hyphen in there, so it looks a little bit different. NVMe only gives us 20 characters. And that mount point that I was talking about before on Xen. NVMe gives us the ability to add what's called vendor-specific information. And so using the NVMe CLI, you can actually get this vendor-specific information. And if you read the first 32 bytes of that, it's a string that is the mount point that you specified on the console. So that's how you can find your volumes. If you're running Amazon Linux, we have a package called EC2 utils. And so this provides a lot of helpful tools for EC2 instances. With the most recent update to the package, we added a couple commands that extract this information for you. And so with the EBS NVMe ID command, you'll get the pretty volume ID with the hyphen that you're used to, and the block device. So we'll extract that for you so you don't have to read the hex and all that. We also added some UDEV rules so that when you attach a volume to a kernel that has this utils package installed, and so you can get it on the most recent Amazon Linux AMI, or you can just update an existing AMI with the new EC2 utils. That UDEV rule will create the symlink that you're used to. So your mount point will show up as devxvdf. Now I recommend that when you create a file system on these drives, that you label them and reference labels when you're doing persistent mounts. And if you have to, use the mount point that you specified in the console, because the NVMe devices actually can move around a bit. So you might reboot, and what was NVMe 1 may show up as NVMe 2 based on PCI enumeration order. So I mentioned I'm not going to go too deep, but I'll go a little bit into what's happening, just to point out some differences in how it impacts EBS. So the Nitro Hypervisor is a lot lighter. There's a whole lot less going on. It's not involved in I/O at all. When you attach an EBS volume, it's attached to the Nitro card, and the Nitro card presents PCI into your instance. That I/O that your application wants to do gets submitted right to the Nitro card. So there's no time spent in the hypervisor. There's no doorbells, no waiting around. And so what we've noticed is on volumes attached, your long tail latencies, we've noticed a decrease in the tens of milliseconds. So there's a huge performance impact just in the latency outliers. So security is important to us, and we know it's important to you too. So for that, we offer EBS encrypted volumes. Now you can roll your own encryption within your instance, but that's going to take CPU away from your instance. With EBS encrypted volumes, all you do is you check a box when you create it, and you can attach it to most instances with no performance impact. And so how do we do it with no performance impact? Well, if you follow the trail and the story that Peter talked about on Tuesday, and Anthony and Matt talked about yesterday, we've been offloading cryptographic operations for a long time in EC2. And so all the cryptographic operations are done in hardware offload. There's a performance benefit because we don't have to use CPU for that, but there's also a security benefit for that because it's not software that we wrote that's touching it. Your EBS data is encrypted next to your instance. So before it even touches the network. So all your data in flight is encrypted. It's still encrypted and remains encrypted when it's stored on the EBS servers in the back end, and it continues to be encrypted while it's a snapshot as well. Now, all accounts can create an EBS volume using the default EBS master key. This master key protects the keys that actually encrypt your volume, so it's envelope encryption from that standpoint. As a best practice, we recommend that you actually create a new master key. Now, there's no downside to using the default key, and it works perfectly fine. It's the same security model. But when you create a custom master key, which you can do through the KMS console, You can define key rotation policies, access controls, and better auditing and logging. So if that's important to your business, then a custom master key is the only way to do that. Once you've created that, you just specify it when you encrypt the volume, either on the console or the APIs. It's just an additional parameter. Now, because EBS volumes persist beyond the life of your EC2 instance, we need to think about the reliability of EBS separate from EC2. So we think about volume reliability in two ways. The first way is availability. And so we define the availability as the ability to access your data, which typically includes our network, service uptime, and other things behind the scenes. Now, in the availability realm, EBS is designed for 5 nines of availability. And we track this consistently. We've got metrics, we're logging, we're auditing, keep a lot of history on this. And we've got extremely aggressive alarms so that we know long before we come close to reaching this 5 nines that we're going to have a problem. Second is durability, or the ability to get your data off the media. EBS has an annual failure rate between 0.1 and 0.2%. Which is significantly more durable than a commodity disk. Those are going to be in the 3 to 6% range. So the way to think about EBS durability is that if you've got 1,000 volumes over the course of a year, on average, you can expect 1 to 2 of those to fail. Hopefully, you'll get luckier than that. Sometimes it'll be a little bit worse, but 1 to 2 is a good average. And that's the 0.1 to 0.2%. Now, we're designed for this without any action on your part. But you can further reduce the probability of volume loss by taking regular snapshots. And so an EBS snapshot is a point-in-time, crash-consistent copy of your data stored in S3, which is a service designed for 11 nines of durability. Now, the first time you take a snapshot, every modified block is copied to S3. Subsequent snapshots are incremental, and only the blocks that you've written and changed since the previous snapshot are pushed. When you delete a snapshot, we keep track of the data that's required to build all future snapshots. So we only delete the data that's exclusive to that snapshot. So I mentioned that taking a snapshot can reduce the probability of volume loss. So it's important to remember that EBS is a distributed system, and your data is sharded across many drives. So when a failure happens, and they do, we're going to need to reshard your data. And when we're resharding data, we prioritize the data that's changed since the last snapshot first. And so with a recent snapshot, you actually reduce the amount of data that has priority. And then if there is a coincident failure as we're trying to reshard your data, we can pull the rest from S3 if we need to. And so by examining the behavior of some of our customers, this continues on the theme of pulling data and analyzing historical data. What we found is that customers that take a daily snapshot have a significant positive impact on their volume AFR. So crash-consistent snapshots are similar to pulling the power cord on your server. Now, most journaled file systems and applications can handle this with no problem. But if your application requires consistent snapshots beyond that, or if you have multiple volumes that you want to snapshot at the same time, you should first quiesce your I/O. And so once you've quiesced, you call the snapshot API. When the API returns success, you'll get a snapshot ID. When you have that snapshot ID, you can resume I/O. You don't have to wait for the snapshot to keep pushing in the background and the snapshot to complete. We've marked that point in time, and any new changes and writes that you make will not be represented in that snapshot. So there's equivalent utilities for Windows as well. Windows also has the ability to use VSS to take application consistent snapshots, and there's some integrations with that. Recently, we integrated EC2 SSM, Simple Service Manager, and VSS in your instances. And so if you're already using SSM, you just need to make sure that you have the right actions, the new actions in your policy, or you can create a new IAM policy, attach it to your instance. And once it's attached to your instance and you've got that policy, if you've got the updated VSS packages, which there's a run command that'll actually help you with that, or they're available in the most recent Windows OMNIs, you can use the create VSS snapshot run command. This can be done through the CLI, the console, custom PowerShell scripts, or I've even seen Lambda functions that'll do it. And so in this example, we're using the console, select the instance, other properties of the command. Once you execute this, the snapshots are going to be tagged with app consistent equals true. just to help you keep a better track of it and you know the status of those snapshots. So another interesting use case. Infor is a customer that runs their SQL Server databases on I2. They need the local instance storage. They need the latency and the performance that provides them. But what they realized that they could do is use ST1 volumes. And I saw a couple confused. Jody mentioned earlier that you could use these streaming volumes for backups. I'm going to explain how that goes. So they use a VSS-aware snapshot utility that backs up to these ST1 volumes, and then they take EBS snapshots of those volumes. And by doing this, they were able to improve their backup speed by 30%. So they don't need to keep as many snapshots in flight anymore. They've simplified their backup strategy and reduced their backup cost by 75%. So I briefly mentioned tags with the VSS integration. For those of you that aren't familiar with tags, tags give you the ability to assign a simple key value pair to your instances, volumes, and EBS snapshots. And so you can group and manage those resources together. One thing that you can do with those tags is activate them as cost allocation tags, which makes that data available through the billing pipeline. So you activate them in the billing dashboard, and then you can generate reports on cost, usage, broken down by those tag values, such as dev, test, backup. And the same data is also visible in the Cost Explorer for additional visualization. Now that we've got a snapshot, what can we do with it? With EBS snapshots, you're able to create a copy of a volume in another availability zone, or even the same AZ, within a region. And this could be useful for load balancing. Say you need to spin up a new front end for your application, bootstrap a new node into a cluster, or maybe replace a failed node, or if you want to set up another disaster recovery cluster. If you use EBS snapshot copy functionality, you can copy those snapshots to another region. So this can help you set up a disaster recovery site across the country, maybe in another part of the world, or even bootstrap into one of the new regions that AWS launches. So we can use building blocks of Lambda, run command, and resource tagging. And we put together templates that help you with this with Ops Automator to build a snapshot lifecycle management system so that you can set policies on your snapshots to take say you want to do a weekly snapshot or a daily snapshot, as well as retention policies, so you'll delete them after a month or whatever you need to do. On many of our current generation instance types, when EBS volumes are attached, and only EBS volumes are attached, you can take advantage of EC2 auto recovery. So what auto recovery is a per instance alarm. And when that fails, or when that goes into alarm, it triggers a recovery workflow. That recovery workflow will reboot your instance, sometimes placing it on different hardware if that's what the failure is. And that new instance is going to retain all of the same configuration data that it had previously. So same instance ID, same volume attachments, IP addresses, et cetera. So the application can come up with no impact or with no extra manual effort required. So a little bit, one bit of housekeeping here. So by default, boot volumes are tied to the life of your instance, and data volumes are not. Now, a lot of times you do want to keep that data around. And so what happens is that when you terminate your instance, the volumes stick around. One thing that I recommend here is that you tag those volumes so that you know what's on them, so that 6 months later you're not trying to do this mass effort to try and clean them up and figure out if you need them or not. If you've got a dev and test workload and you want us to, or for some other reason you want us to clean up those volumes automatically, you can set the delete on termination flag to true. And when you terminate that instance, what will happen is we'll sweep all of the volumes that have that tag set to true and delete them automatically for you. So that'll reduce your costs, reduce your management requirements. So probably the area that we've collected the most amount of data and the most metrics on EBS volumes is performance. And so as Jody mentioned earlier, this has helped us define a lot of our newer products that work just for your workloads, whether they're transactional, throughput, or some sort of mix of both. Now, these recent volumes that we defined do have performance characteristics and define performance criteria. And it's important to know how we actually measure IOPS or throughput depending on your volume type. So if you're doing random I/O to an SSD, one of our SSD-backed products, the I/O size is based on 16 kilobytes. So that means that if you're going to submit a 4K IO, we're still going to logically count it as a 16K IO for accounting purposes. The hard drive back volumes are designed for throughput, and so to encourage larger writes and to make sure that larger writes are actually happening, we account on a 1 megabyte size. Now, to help sequential operations, not everything's small random. We'll logically merge sequential IOs. And so what this allows you to do, potentially you can provision fewer IOPS on your provisioned IOPS volumes, and it also maximizes the amount of burst capability that you have. Now, this is logical merging. We don't hang on to your IO, wait for the next one and the next one and the next one to complete before we account and complete them all. We just keep track of where those IOs were. If we notice that they're sequential, we won't take any more tokens out of the limiters. And so in general, if you're doing sequential IO, you still want to submit as large as you can, but we'll try and keep track of it as best as we can. So a couple examples. If your application is doing random IO, and by random, it means an IO that has an offset that's not adjacent to the previous IO, so somewhere on your disk. We'll take each one of those IOs, put it in a boxcar, and just 4 IOs. Now, if you're submitting sequential IO, say we're doing 4 64K IOs to an SSD-backed volume. We'll pack those into a single boxcar and only count it as 1 IO. So we'll merge those together. They'll complete when they're ready. We won't wait for them. But it'll only count as 1 IO against the throttles. Now, for our hard drive back volumes, we'll gather up to 1,024K. So if you submit 4 64K IOs and you continue submitting 64K IOs, we'll still count that as 1 single IO. The reverse is true for our SSD products. If you submit a large IO, for accounting purposes, we'll split that up into 4 boxcars and take 4 tokens out of the bucket. So the reality of the world is most applications don't do purely sequential. They don't do purely random. Typically, it's a mix of both, biased one way or the other. And so here's a good example of what can happen in ST1 and SC1 volume. Your application submits a couple large IOs. We'll merge those together into 1 bucket, a couple random IOs, and then a couple more sequential IOs. And so you submitted 6. We counted it as 4, so we helped you out a little bit. But it's still counting 4 megabytes per second of burst, even though your application was only able to get 1.5 megabytes of data. So Jody told the story earlier about how we built GP2 volumes. I'm going to quickly go through the burst bucket. I used to stand up here and spend about 15 minutes on this, but I'll give you a little trick at the end so you don't have to get out your slide rule. All of our volumes with burst operate on a token bucket model. For GP2, your volume is always accumulating at a rate of 3 IOPS per gigabyte. Bucket's a fixed size, and then you can spend those credits at 3,000 credits per second, which is the burst, or for a volume that's larger than that, it'll be your 3 IOPS per gigabyte. Here it is in graph form, if you don't like my animation with the bathtub. See the baseline IOPS in green? Smaller volumes that are less than 1,000 gigabytes get a burst bucket. And then so as an example, we've got a 300 gigabyte volume here. It's got a 900 IOPS baseline, and it bursts up to 3,000 IOPS. Now the question that I do often get is, how long can I burst? Now, since the bucket is constantly refilling, the token bucket is constantly refilling based upon your volume size, the amount of time that you can burst actually increases as your volume grows. Now, our smallest GP2 volumes can burst for 30 minutes, or enough for a couple reboots, maybe even a kernel build in there, especially on one of our new C-series instances, C5 instances. As your volume grows, the amount of time grows. So our 300 gigabyte volume can burst for 43 minutes in this example. And as we get larger and larger, to a 950 gigabyte volume, say, it's 10 hours, and then as it approaches, it'll approach your 3 IOPS per gigabyte limit, and you won't have burst anymore. It'll just be that all the time. Throughput volumes work about the same. We just measure throughput instead of IOPS. The other difference with our throughput volumes is the bucket grows as your volume grows. And so let's take a look at what that looks like in graphical form. You'll see that the burst actually increases pretty quickly. up to the maximum of 500 megabytes per second on ST1 volumes. And then when you get to the 12.5 terabyte size, your baseline and your burst match, and so that's when we end up with your baseline as being the dominant factor there. With an 8 terabyte volume, you have a 320 megabyte per second burst, or 320 megabyte per second baseline and a 500 megabyte per second burst. SC1 volumes designed a bit more modestly. Still good, though. If you look at the base, that's at 250 megabytes per second. Most commodity hard drives, you're going to get about 150 plus or minus, depending on the workload. So you're going to get pretty good performance out of SC1. The important thing to note here, though, is that even at the largest volume size, the baseline does not get up to the throughput. So you're going to have some cold periods to get to refill that burst, the burst bucket. Difference between sequential and random. So if you're going to do large sequential workload for 3 hours on an SC1 or ST1 volume, you can transfer almost 5.5 terabytes of data. So you can burn through your entire drive pretty quickly there. Instead, if you're doing a small random workload, same amount of time, same 3 hours, you only get 87 gigabytes of data. SC1 volumes are similar with lower levels there, just because of the more modest workload they're designed for. So here's the trick. We introduced a burst balance metric. You don't need to get out your slide rule, like I mentioned. Just size your volume for your average workload. Let the burst balance take care of the peak, and then monitor it using the burst balance metric. And so here's an example of 500 gigabyte volume, which if you do the math, we get 1,500 IOPS of baseline and 3,000 IOPS of burst. And I ran a synthetic FIO benchmark. Now, benchmarks aren't indicative of real workloads. They're great at showing what max and peak performance is, which is what I wanted to do here today. But you should really be benchmarking with your typical workload. That's going to give you a better idea of what size volume you're going to need. So I ran this test for an hour. And you can see that I was getting 3,000 IOPS in orange there. And as I was getting 3,000 IOPS, my burst balance was slowly decreasing. And I was decreasing at the 3,000 IOPS rate. And then when it got to 0, the volume performance dropped to 1,500 IOPS. There we go. Now, how do you know what I/O size your workload is driving? So you can use perfmon on Windows or IOStat on Linux. Now, this is measured in sectors. You can see here I'm driving about 246 sectors, which is roughly 1 megabyte. So I'm probably doing some random I/O in there occasionally. But I'm getting pretty close to that 1 megabyte that I'm interested in. And then you can get the same data, too fast, get the same data out of perfmon. So you can also look at CloudWatch. Now, CloudWatch, you can show the average write size. And here we'll see it's 128K. And for architectural reasons and how things get displayed in CloudWatch, this is what we see on the EBS backend, even though your application and your instance may be submitting 1 megabyte IOs. So this is about the maximum that you're going to see in CloudWatch. You can overlay this with your burst balance metric to see if it's depleting, and that'll help you determine if you are actually submitting those sequential IOs. If you see something in 64 or less than 128K, you're probably doing smaller IOs that we're not able to merge. And again, if you look at your burst balance metric overlaid with this, you can see if they're random or sequential. Now, in some cases, you might be stuck around 44K. This is an interesting artifact. If you're running on one of our older instance types, or if you're running an older Linux kernel, there were some changes around the 310 kernel in Zen that allowed you to submit greater than a 44K IO. You could submit up to a meg, and I'll show you how to change that in a moment. All of our current generation instance types support the new variety. So if you upgrade your kernel to a 3.2 or better and you're running on a current generation instance, you can actually get more than 44K. Now, the caveat here is if you're running Windows, you're stuck at 44K unless you move to one of our Nitro instances. So if you're throughput or performance tuning and you're doing a heavy read throughput workload on ST1 SC1, recommend that you increase your read-ahead buffer. And so this is per volume. Defaults to 128K. Again, this is actually set in sectors on Linux. If you do this and you run a random workload on your volume, you're not going to be happy. Because what's going to happen is the kernel, if you submit a 4K IO, is going to say, he wanted to read a megabyte. And so I'm just going to grab that whole megabyte and completely deplete any burst bucket on an SSD volume, for example, on a GP2 volume. If you're running on one of our Zen instances, here's how to increase the maximum IO size. So if you're doing any kind of throughput workload, this is a per instance configuration. Now, the default is set to 128K, which is a pretty decent balance between getting enough throughput through and taking memory out of your guest. Now, just to be confusing, this is measured in 4K memory pages, not sectors. One of these days, Linux will be consistent. There's the way to set that. They changed the parameter in 4.6 as well. Now, you don't want to do this if you're on a smaller instance type, because what this does is it sets aside that memory ahead of time when you attach that volume. So 32 IOs times 1 megabyte, if you increase this to a megabyte, is going to be 32 megabytes for every IO, which isn't too bad on an R4 or a C5. But if you're trying to do this on a T2 micro, you're going to pretty quickly run out of memory for your application. So the next input to volume performance is EBS-optimized instances. And with EBS-optimized instances, we set aside separate bandwidth just for EBS, which is separate from your application. And so this is enabled by default on EBS, on instances with EBS on Nitro. And so this started back in C4 that it's enabled by default. And that's because we were able to set aside a separate physical network connection just for EBS. If you're on one of our older instances and you've launched without EBS optimized, you can enable it by stopping your instance, changing the attribute, and then restart your instance. So if you are on when you are on an EBS instance, it's important to consider that EBS optimized bandwidth. And so if you attach a 2 terabyte volume and you're doing an IOPS workload, 16K IOPS workload, that GP2 volume should be able to do 6,000 IOPS. Now you're on a C4 large and you notice that you're only able to get around 4,000 IOPS. If we look at the EBS-optimized throughput that's available on a C4 large, you do the math at 500 megabits per second, it comes out to roughly 4,016K IOPS. And so you're not going to be able to get the full volume performance out of that volume. So if you need that 6,000 IOPS that 2 terabyte volume delivers, you probably want to go to a larger instance, say a C4 2 extra large, which has double the bandwidth available to EBS. Now with C5, continuing on using data, we took a look at how customers use EBS-optimized instances. And one of the things that we realized is that a lot of customers on smaller instance sizes have bursty workloads. Noticed it in volumes. We also noticed it in aggregates of volumes. And so we were able to change the way that we thought about EBS-optimized for our smaller instances and added a burst capability. And so on C5 large, extra large, and 2 extra large, and this is also M5 as well, you can burst up to the specifications of a C5 4 extra large for 30 minutes. And that gets reset automatically every day. So even if you're continuously driving max throughput, you'll get that full 30 minutes every day, once a day. And then it drops down to the baseline throughput of 525 megabits per second in this example. So if you need more storage than 16 terabytes, if you need more throughput than 500 megabytes per second, and if you need more IOPS than 20,000, you can stripe a couple volumes together. But if you're going to RAID, recommend that you avoid reading for redundancy. So EBS is a distributed system. We already shard your data and replicate your data on the back end. And if you're going to RAID, you're going to reduce that EBS-optimized bandwidth that's available to your application. So if you're doing a straight mirror, you're going to cut it in half. If you're doing some sort of erasure coding like RAID 5 or RAID 6, you're going to get 20 to 30% less. So another question that I often get is, what about EBS volume initialization? And how do I get the maximum performance out of my volume? So if you have a new EBS volume, just attach it to your instance. It's ready to go. You'll get full performance out of it. If you've got a volume from snapshot, EBS pulls that data out of S3 in the background. And we do this without you having to worry about it. And if you try to do an I/O to something that we haven't pulled yet, we'll prioritize pulling that data from S3. So one of the things that you can do if we're not loading it fast enough is you can tell us and signal to us that you want to use some of your volume performance to pull the data from S3 faster. And so to do that, you can do a random read across the volume. Now, recently for IO1 volumes, we do this automatically in the back end. So if you're not using your IO1 volume, we'll go ahead and use all the volume performance available to pull that S3 data. We noticed about a 10x improvement in snapshot load times. Now, when you're doing this initialization, we recommend a high Q-depth random read across your volume. That's going to give you the best performance. So here's an example FIO command. When you start this, it's going to be super sad. It's going to give you some estimated time of completion in about a month and a half. That's because we're pulling at S3 speeds, which are measured sometimes in seconds. As we pull the data, the IOs are going to return faster and faster and faster until you get your full volume performance. And so you don't have to let this command finish. We're going to pull the data, and we're going to pull more data than you've requested here. And really, it's in the neighborhood of 20 to 30% where you'll start to see your full volume performance. And you can monitor the latency that you're getting or the IOPS, either using CloudWatch or using tools within your instance. And when you see the expected volume performance, you can just go ahead and kill this, and your volume is initialized as you need it to be. So you want to select the right volume for your workload. And if you mess up, we've got elastic volumes. You can change it to a new volume type without having to stop your instance. Select the right instance for your workload. Make sure it's got enough EBS-optimized bandwidth to support the needs. Take snapshots, tag those volumes so you know what's on them. And if your requirements demand it, use encryption. So we've got some new storage training if you want to dive a little bit deeper. And Jody and I will be hanging out to answer questions. Thanks.